Welcome back to my second video of my Factorio series. Previously, we have constructed a circuit network that takes in a chest of various items and outputs these items into a belt such that the items are fully stacked. We used the decider combinator to check whether each item inside the chest has a count of greater than or equal to 16. Now, a lot of people have problems when they download a blueprint from the internet to understand what the circuit is doing, because in game it is difficult to see where the wires are connected, or you need to open up each entity to check the conditions inside them, and after you open up say 5 entities, you already forget what the first one did. So here I propose an easy way to visualize the circuits using a graph. So for each entity, we would create a node or vertex. 2 vertices are connected if there's a wire connecting them, and we set the color to match the color of the wire. Now, based on this implementation of the circuit, we can draw a graph of the circuit network, and over each wire, we can record the signal of the wires and write a quick comment on what signal is being stored. Here's a quick summary of all the entities we covered last time. A source is an entity that generates an uncolored output, which means that it generates 2 identical signals in both its red and green channels. A target takes in an uncolored input, meaning that its input is treated as the combined signal of both its green and red channel. And if a condition holds about this input, then it will enable certain behavior. Next, we have a decider combinator, which takes colored input, meaning it is able to distinguish the colors of its input, and if certain condition holds about this colored input, then it will generate either a pre-programmed constant or the exact same value as the input signal as an uncolored output. Now I need to make one note here that each signal, the wildcard signals for the decider, can act differently from what I've written here, and this will be covered in a future video. An arithmetic combinator generates an algebraic function such as multiplication, addition, and exponents of a colored input as an uncolored output. Finally, the selector combinator is a mystery. Now in today's video, we're going to cover something called input delay for the combinators. When a combinator or a target receives an input, it will take them 1 tick in game for them to react. In order to see this on the graph, we can label the arrows by T1, T2 to indicate which ticks they have received the signal. This will help us to identify any delay that could be caused in the initialization of this circuit. So in this example, we know the chest is only affected by the inserter, and the inserter will not do anything to the chest until it receives the final signal. So the input delay will not affect the system. So let me give you an approach of the recycler stacking problem, which is influenced by this input delay, and show you how we visualize this delay. Let me begin with the chest that reads the content and outputs into 2 channels. I take one of the channel and convert everything inside this channel to -15 and add it to the other channel that is from the chest. If we set the filter to this total signal, then it appears that the combined signal has an item with value greater than or equal to 1 if and only if the chest item -15 is greater than or equal to 1, which happens if there are at least 16 items inside the chest. So this seems to solve the recycler stacking problem. But if we draw the graph for the circuit and label the arrows with the ticks that the signal is received, we will see that for the inserter, it receives the red signal in time 1 and receives the green signal in time 2. Now you will see that in tick 1, the inserter will receive the red signal, which is not subtracted by 15 yet, so it will take out the item in the chest. And when the second -15 signal reaches the inserter, it is too late because the inserter has already acted. So we did not achieve what we want. And in general, when you create a circuit network, you want to ask how long does it take for the initialization of the circuit, and could the input have changed its value before the signal has reached the target. If it does, then this circuit might not behave as you would expect. Now, I claim that if you know that your circuit inputs will not change within n ticks from the previous change, then you can have a chain of at most n combinators and targets such that the time delay caused by the combinators will not cause any issues. Now that you know the existence of these delays, it's time for us to use it for our benefit. Here's a question of constructing a circuit which output a value t at the tth tick after initialization. This is a very common timer implementation. You begin with something called a memory cell. It is an arithmetic combinator that outputs into its input. So you'd have a loop inside your graph, and the combinator simply takes the same value multiplied by 1 and outputs the same value, which means if we only have the red channel, this value will be repeated forever. And now you take a green signal with a value of 1 and add it to the input, and because the input of an arithmetic combinator is uncolored, meaning it will take the combined signal of these two colors, it will add this 1 to the total value of t in every single tick. This is why it counts up 1 in every tick and achieves the timer effect. Now here is the graph, and you can very easily see there is a loop which utilizes the fact that we have delays. Now sometimes you want your timer to reset at some point to achieve a repeating effect. So here we want a timer such that if the condition C0 is met, we keep counting, but as soon as C0 disappears, we stop and reset the timer. Here's an alternative implementation of the timer using only one decider combinator and allows us to implement this condition, C0. It takes in a value G1 and has two parts for output. First, it outputs the exact same value as the input, then it adds 1 to the output, and then it feeds it back to the input again to achieve a counting effect. But we only count if C0 is true, and if C0 is not true, there would be no output, which means the timer resets. Again, in the graph, you can see a loop on the decider combinator, meaning that there is some time-related shenanigans going on. The next scenario we want to cover is called a state change detector. So if I have a signal S0, I want a circuit that outputs a specific signal if a condition C0 is true about S0, but for the previous tick, and another condition is true about S0 for the current tick. So I want to check both ticks for certain conditions. You would want to do this if you want to check whether the signal is increasing or decreasing, and then you want to compare this with the previous value. Or if you have a timer that counts up to 59 and then goes to 0, and at that moment you want to increase the second counter or the minute counter by 1. The approach is that you want to record the value of the previous tick using an arithmetic combinator that outputs exactly what it receives, but this causes there to be a delay of the signal. Here is how you would implement the circuit. First, you have some kind of input, say coming from a green signal. You would pass the green signal to either an arithmetic combinator and a decider combinator, so that the green one represents the current signal. But when passed through the arithmetic combinator, you output exactly the same thing into a red channel, and this red channel will store the delayed version of the signal. You want to check whether condition C0 holds for the previous tick and whether C1 holds for the current tick. And you output the desired output in that case. In this example, I have a light that turns on if this state change is detected. Now for our last example of the day, let's look at something called a maximum recorder. The idea is that you're given a continuous stream of signals, and we assume that we have only positive values, which could potentially change its value at every tick. Now we want to record the highest value that's showed up so far. The approach you come up with is usually first store the high value in a memory cell, and then compare the current value with the high value. And if the current value is larger, you can replace the highest value with the current one. Or here, what we do is we add the difference to what we already stored. Now here's a naive implementation of what I just said. You start with an input passing through the channel G1, and we have an arithmetic combinator that records the highest value so far. This is the memory cell, and the highest value is recorded in R2. Now to get the difference between the current value and the stored value, we take -1 of the stored value and combine with the current value. Now if the combined value is greater than 0, that means the difference is greater than 0. That means we should replace the old value with a bigger one. So we pass the difference to the memory cell so that the difference is added to the memory. Now down here you have a graph representation of this. The third combinator is the memory cell. The last one multiplies -1 to it. And for the decider, you get both G1 from the input and the inverted memory, the inverted high value. And if you have a difference, then you pass it to the memory cell. And if you want to extract the highest value, you can simply connect a red wire to extract this R2 channel. Now a problem you'll notice if you try to implement this in game is that the decider receives its input at the first tick, but the other input would only be updated at the fourth tick. This means between the first and the fourth tick, the decider would still be receiving the input and comparing it with an outdated high value. And this is a problem with the delay that commonly shows up when your input varies rapidly. In order to fix this, we first notice that the circuit is only vulnerable to the delay if we receive the signal continuously in every tick. And on the other hand, if we only receive the input every 3 ticks, then the delay would not cause a problem, and we're going to be comparing with the correct updated high value. Therefore, we can create 3 copies of our circuit and pass the input to each copy once every 3 ticks. And that gives you 3 recorded high values. So for the final value, you just need to take the maximum of the 3 values. So here's the circuit. What we do is we set up a timer that repeats every 3 ticks, and we set up 3 deciders for I equals to 0, 1, 2. that takes in the input and the time and the high value of the ith system. Then you say if the time is equal to I, so if we are in the ith tick, if the difference is greater than 0, then we can pass the difference to the memory cell. And the rest is the same as before, but in the end, you will get 3 recorded high values, and you want a circuit that returns the maximum of these 3, and this is a very easy implementation that you can do it for yourself. Now this is the end of the video. My goal is to develop these kind of tables where you can fill in the information for the circuits and make it easy to read. So I hope you find my graphs and tables more clear than what you see in game. But if you do want to see something in game how it works, here is the build for my example. There's a mod called Circuit Visualizer to represent your red and green wires. And here at my input, I have set up to be a timer that repeats once every 120 ticks, which means my maximum recorder should be recording 120 in the end. If I reset this, you'll see it does count up to 120 and then hold this value. Well, thank you very much for watching. Bye!